Mechanical fatigue. This is the second and last damage mechanism under mechanical and metallurgical failure mechanism as per the API 570 Piping Inspector exam syllabus. Bend a small wire back and forth. After some time it will break. If you increase the degree of bending, then it will break with less time. But always it will be unpredictable and we cannot say when it will break. Welcome to Module 2, Part 4 of API 570 Piping Exam Study Guide. Description of damage. Read the complete description from the codebook. The points that are here are: it is a mechanical form of degradation. It occurs to a component exposed to cyclic stresses for an extended period. 2 points are here. One is cyclic stress and the second is extended period. Failure is sudden and unexpected for mechanical damage. Mechanical loading or thermal cycling can cause this damage. 2 loads that cause mechanical fatigue are mechanical loading and thermal cycling. Please note that here the cause is thermal cycling and not thermal fatigue. There may be a confusion in the options when these two options are given, that is thermal cycling and thermal fatigue. Here the option is thermal cycling only. The damage occurs well below the yield strength of the material. Well below the yield strength. Normally, a material fails when it is loaded above the yield strength. But here it fails below the yield strength when fatigue happens. That is why the damage is unpredictable. Affected materials. All engineering alloys are subject to mechanical fatigue. Engineering materials are affected. All the engineering materials are affected. This is an important point. The stress levels and number of cycles necessary to cause failure vary by material. Critical factors. The predominant factors that cause mechanical damage are geometry, stress level, number of cycles, and material properties. In the material properties, strength, hardness, and microstructure are the factors that are important. Here, please note that only 3 of the mechanical properties are acting as the critical factor for mechanical fatigue. They are strength, hardness, and microstructure. Critical factors. Fatigue cracks usually initiate on the surface at notches or stress risers under cyclic loading. Due to this reason, design is the most important factor in determining a component's resistance to fatigue corrosion. The code lists the surface features that can act as stress concentration points and thereby the reason for fatigue cracking. These features become the crack initiation points also. Some of the features are mechanical notches, that is sharp corners or grooves, keyholes on drive shafts of rotation equipment, well joint, flaws and or mismatches, tool markings, grinding marks, lips on drilled holes and corrosion. This is the reason behind instructing for smooth transition of welds to base materials. Grinding marks on the surface during fit-up pleat removal or edge grinding of welding are to be removed as they can act as stress raisers and may cause fatigue crack. Metallurgical issues and microstructure. A new term called endurance limit is mentioned while discussing the metallurgical issues and microstructure related to mechanical fatigue. What is endurance limit? Endurance limit is the stress level below which an infinite number of loading cycles can be applied to a material without causing fatigue failure. Here it is to be noted that if the stress are below the endurance limit, that is below the endurance limit of material, mechanical fatigue damage will not occur. Description of damage. Read the complete description from the code book. The points that are here are: it is a mechanical form of degradation. It occurs to a component exposed to cyclic stresses for an extended period. 2 points are here. One is cyclic stress and the second is extended period. Failure is sudden and unexpected for mechanical damage. Mechanical loading or thermal cycling can cause this damage. 2 loads that cause mechanical fatigue are mechanical loading and thermal cycling. Please note that here the cause is thermal cycling and not thermal fatigue. There may alloys with endurance limit are titanium, carbon steel and low alloy steel. Remember, below the endurance limit, fatigue cracking will not occur regardless of the number of cycles. Materials without endurance limit are 300 series stainless steel, 400 series stainless steel, aluminum and most other non-ferrous alloys. This we have to remember: materials with endurance limit and materials without endurance limit. For materials with endurance limit, there is a relation between the endurance limit and ultimate tensile strength, that is UTS. Endurance limit divided by UTS is equal to 0.4 to 0.5, or otherwise we can say that endurance limit is 40 to 50% of UTS. UTS of a material can be found from mechanical design data books, and thereby we can predetermine the endurance limit. If the endurance limit is defined, the design stress limit can be easily finalized by the design engineer. For those materials that don't have the endurance limit, like aluminum, 300 series SS, etc., the maximum cyclical stress amplitude is determined by relating the stress necessary to cause fracture to the desired number of cycles in the component's lifetime. Typically, this is fixed to 106 to 107 cycles. That is, if the item is, what is the stress required to break the item in 106 or 107 cycles, that is determined. That means cycle is fixed in the x-axis of the SN curve, and the point where the vertical line touches the graph of that metal is noted. The stress corresponding to that point is the limiting stress for that alloy. This much details are not necessary for the exam point of view, but it will give an idea and will help you to answer when questions related to some practical aspects are asked. The main point to remember here are endurance limit is 40 to 50% of UTS. If the endurance limit is not there, 106 to 107 cycles are fixed and the stresses corresponding to it is considered as stress without mechanical damage. Inclusions found in metal can have an accelerating effect on fatigue cracking. Dirty steel, older steel and weldment are as often have inclusions and discontinuities that can degrade fatigue resistance. Finer grained microstructures tend to perform better than coarse grained. Heat treatment can have a significant effect on the toughness and hence fatigue resistance of a metal. By heat treatment, the grains are refined. As we discussed, thermal cycling and mechanical loading can cause mechanical fatigue. So, equipments and units having these two conditions are prone to mechanical fatigue. Thermal cycling happens in coke drums, auxiliary boiler, etc. Mechanical loading happens in pressure swing absorbers or hydrogen purification units. Rotating shafts of centrifugal pumps and compressors are also prone to mechanical fatigue. Vibration of small diameter piping are also affected by mechanical fatigue. The signature mark of a Fatigue failure is a clamshell type fingerprint that has concentric rings called beach marks emanating from the crack initiation site. Cracks nucleating from surface stress concentration or defect is identified by single clamshell fingerprint. Cyclical overstress of a component without significant stress concentration causes multiple points of nucleation and thereby multiple clamshell fingerprint occurs. Please note these two conditions of single clamshell fingerprint and multiple clamshell fingerprint. For materials with endurance limit, there is a relation between the endurance limit and ultimate tensile strength, that is UTS. Endurance limit divided by UTS is equal to 0.4 to 0.5, or otherwise we can say that endurance limit is 40 to 50%. The best defense is a good design. Select a metal with a design fatigue life sufficient for its intended cyclic service. Minimize grinding marks, nicks and gouges on the surface of components. Use low stress stamps and marking tools. These are some of the prevention mitigation methods for mechanical fatigue. One of the main causes for the mechanical fatigue is mentioned as grinding marks. So please note that point. As fatigue crack initiates from the surface detection NDT methods to be adopted. Penetrant testing, MT and SWT can be used to detect fatigue cracks at known areas of stress concentration. Known areas are scanned by the NDT methods for mechanical fatigue cracks. Vibration monitoring of shafts is also a monitoring mechanism. Visual testing of small diameter piping to detect oscillation is another method of inspecting and monitoring of mechanical fatigue. Metallurgical issues and microstructure. A new term called endurance limit is mentioned while discussing the metallurgical issues and microstructure related to mechanical fatigue. What is endurance limit? Endurance limit is the stress level below which, and if you felt that the video is useful, please share it with your fellow engineers and groups. Please subscribe the channel for updates. For course notes, please visit my blog. Thank you for viewing this video. Thank you.